Hello and welcome back for another VMK in the C++ series. This VMK is going to focus on how to use the Microsoft Visual C++ Debugger whenever you're trying to figure out what is wrong with your code. So let's get started. I'm going to be using Visual C++ 2008 Express Edition, but you'll see the same kind of features present inside the 2005 Express Edition as well as the 2003 .NET. To get started, I'm just going to create a simple program under New Project, Win32 Console Project, and I'll call this Debug. Under Application Settings, I'm going to have Console Application selected. I'm not going to use precompiled headers, so I'm going to deselect that and select Finish. Okay, so here's our main entry point into our code. First, we need to write some code in here so that we can have something to debug. Let's just do some simple printf statements. And maybe we'll have a for loop. Oh, don't forget a carriage return at the end here. Alright, we can go up to the menu here, select Build Solution. Everything succeeded, and we'll press Control F5 on the keyboard to run our program and see the output in our output window. We see we have Matic nose at the top, and then line 0, line 1, all the way down to line 9. And then we have press any key to continue. So our program's up and running. Great. What I want to do is I want to take this for loop and put it inside of a separate function. So I'm going to create a function up here. It's going to return nothing, so it's going to be a void. And I'll just name it foo. And we're just going to take this and put it inside there. And then down here, we're going to call that function. So if we press Control F5, run it again, exact same output. However, the behavior of the program is slightly different now. It starts here. It displays this to the screen, calls this, so we go into here, runs through here, and then we return back from the foo function to then return out of our main. Now let's take a look at our debugger. To start the debugger, we need to press the Start Debugging button, which is usually the triangle located up in the menu bar. If we do that, you notice that the program runs, but immediately closes. It closes because it's finished and there wasn't anything else for the program to do. If there was a key entry or the program was waiting for some sort of input, it would have waited until the program finished. But because all we're doing is displaying to the screen and then returning directly out of our program, there isn't anything that the program has to do once it's done, so it just closes the application. To slow down the debugger, or to be able to see what's going on, we need to place a breakpoint into our code. And to do that, all you need to do is go into this little section here on the left-hand side and click with your left mouse button. You'll see a little red circle appear to specify that you've placed a breakpoint in your code right here. One thing I forgot to do earlier is to turn on my line numbers for our codes. So under Tools, Options, so under Text Editor, C++, there's a checkbox here for line numbers. I'm just going to turn that on just so that there's some line numbers for you guys to follow along with. Okay, on line 14, I've placed a breakpoint. Now when I hit the Start Debugger, notice that the program runs, but it actually stops right here. And if I take a look at the output, there isn't anything in the output window yet because we haven't printed anything to the screen. Again, I'm going to take this and stick it over on the right-hand side because that's where I like to have my Solution Explorer located. When you're in the debugger, we have some additional options to us. We have this window down here, which is currently selected to Autos. And Autos means these are the current variables that you may be interested in figuring out what they currently have. you notice we have argc and argv. These are the parameters that get passed into our program when the application starts. We have locals, which are similar to autos, but these are only the variables that are local to our current scope. We have threads. These are which threads are currently running. Modules, and also a watch window. A watch window is handy because you can type in which variables you're interested in, and it doesn't have to be the ones that are listed under autos or locals. It could be anything that you're really interested in. Over here in this section we have the calling stack, your breakpoints, and the output. So now let's go into the main section of our code. Our execution is currently located where this yellow arrow is pointing. It has not executed this line of code yet. That's why we don't see anything in the output window. To make the code run and actually execute this, you have a number of options. You can use these tools over here to step into, step over, or step out of. And the shortcut keys are F10, F11, and Shift F11. These are very handy to memorize. F10, which means step over, means take this code and execute it and go to the next line. We're not interested in going into this function called printf to see what it does internally. Instead, we just want the output from it. So let's hit F10 on the keyboard. We actually executed this line, and now we're waiting over here to execute this next command. If we go to the output window, we see we have Matic nose displayed to the screen because that's just what got executed. Now, if I press F10 here, foo gets executed and we go to the next line of code. Notice we didn't go into here to take a look at what happens inside of the for loop because we pressed F10. The output shows that we did output all those 10 lines of code to the screen. We can finish our debugger just by hitting the continue button. It's going to finish executing our program and closing our window. Let's rerun the program again. This time hit F10 to execute this line, but instead of hitting F10 this time through, let's hit F11. F11 again is step into, as shown here. You notice now, instead of doing everything that this function does, we go into the function to begin executing it. Hitting F10, we can go line by line through this code here. So we go F10, 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 F10. So we've just executed 2 times this line of code here. In the output window, we can see we have line 0, line 1. Every time I hit F10, it's going through and executing 1 line of code at a time. If we go take a look at our locals, we can see the I value, which is a local variable, currently has a value of 4, as shown here. If I press F10 again in here, you can see it's incrementing because we're executing through this for loop 1 at a time. The other handy thing is you can highlight over top of a variable and it'll show you the current value of that variable. If this variable is an array, then all the components inside of that array will be shown inside of this little tooltip. This works a little bit differently in 2003, where the values don't actually get shown very nicely, but this was fixed in 2005 as well as 2008. So that's the difference between F10 and F11. Now, Shift F11, which is step out of, means, okay, I sort of understand what's going on inside of this function. I don't want to keep pressing F10 to see everything execute 1 at a time. I'm satisfied with what this function is doing, so I want to go in and step out of this function, which means go to the next line after the call to that function. So then we go down here to the return statement. That's what step in, step over, and step out of does. Okay, let's hit continue to finish running our application. There's another way to navigate the control of your program without using the F10 or F11 keys. Instead, you can use the mouse. And let me demonstrate this now. We're going to start a program here, and we're waiting right here at the very beginning of this statement. If I know that I want to go into our code inside of this for loop, what you can do is just select the line of code that you want to go to, right-click, and select Run to Cursor. The program will then continue executing, and it'll only stop when it gets to your cursor location, which you see happened right now. The I value is set to 0, and the execution has not executed the printf function call yet. You notice it displays Matic knows, but it didn't display line 0 just yet. If I hit F10, it's going to display line 0 to the screen and then continue on inside of the for loop. So that's another way you can navigate through your code. You can just right-click, select where you want to run your code to, and it will run to that location and then stop when it gets there. If you make a selection of some place to run to, but the execution doesn't get to it, then your program may actually stop running because it didn't reach your cursor. So for example, let me demonstrate this. I'll create a Boolean variable, VMK, and I'll set it equal to be true. I'll make an if statement here, VMK, else now if we run the program and we choose to run our cursor all the way to this location, notice that the execution goes down to here, and when I press F10 it continues on normally. However, if I try the same thing and I say run to cursor location right here, notice that nothing appears to happen, and that's because when I chose to run to this location, the execution didn't actually go here, it instead went here. So it never reached the location where the cursor is, which means the program went to return and then it exited. So when you are using the feature to run to cursor, you have to make sure that the program will actually get to the location where you've chosen the cursor to be. Now let's take a look at the calling stack. I've showed you where it shows up whenever we run the debugger, but let's create another function to demonstrate its uses. I'm going to create the second function, and I'll call it foo2, and it's going to do something similar where we're going to display just some lines of code here, and let's say we'll just show 5 lines of code. At the bottom here, we're going to call foo2 so that our execution is going to go inside of foo2, and then display this. When we run our program, we see the regular output. Matic knows, 10 lines of code, 5 lines of code, and then OK. Now let's place a breakpoint inside of foo2. When we run our code, we break at the first breakpoint, so let's quit that out. Let's remove things out of the watch window and take a look at our locals. We'll continue running until it gets to the next breakpoint, and the next breakpoint happens to be inside foo2. If we click on the calling stack, we can now see how we got to this location. We first came from main, then we called foo, and then we ended up in foo2. So we know that to get to foo2, we had to come from foo, and we came from main. So just by looking at the listing of function calls here, we know how we got to this location. This is very handy whenever you're trying to debug your program and you're finding that your program is crashing. Just by looking at the call stack, you can figure out in which order certain functions were called in hopes that that will pinpoint where the bug is located. Another very handy window within the debugger is the immediate window shown here. If you don't have this tab down here, you can get it by clicking on Debug, Windows, and then selecting Immediate. Inside of this window, you can perform any kinds of operations that your compiler would normally perform, and you can see the output of those operations. So for instance, if you wanted to know what the value of I is, you can just type in I and press enter. Notice that I is currently equal to 0, so it displays 0. If we run our code for a couple more loops here, you notice I changes to 4, so now if we do the same thing, type in I and press enter, we have 4. But you're not restricted to just having the regular locals or values that you can type inside of the watch window. We can also pick off the value of I within the watch window, but inside of the immediate window you can do extra math. So for instance, you could do something like 10 times I plus 5. it automatically calculates 10 times I plus 5 for you and shows you the result. Let's demonstrate this a little bit more. If we go in here and create some other variables, like let's say an integer, a global integer, and I'm going to set it up to be equal to 100. Again, I'm going to run the code using the debugger, and inside of the immediate window here, what I can do is I can, for instance, say, what is the value of our global variable? Well, we know that it's currently equal to 100 because that's what we set it to, and we can place it inside of the watch window quite easily just by right-clicking on that and selecting Add Watch. You can do this with any variable inside of your program. For instance, if I wanted to add VOK, we can add that to the watch window as well. Because execution hasn't gotten to this point, though, we see that there's a little exclamation point saying that VOK not found. It will be found once the execution goes past here and this variable is initialized. But until then, this variable is not declared, so there is no value that is associated with. Now, going back to the immediate window, we can use our variable g_I, and for instance, we can add 12 to it. So now we can see that the output is 12. We can take g_I and make it equal to 50. As soon as we do that, the variable updates inside memory. So now g_I is no longer 100, it's 50. We have direct access over all of our variables in memory using this immediate window. So you can go in here, change variables at will during runtime, just to make sure that things run the way you expect them to. And to demonstrate this, let's go down to here. Oh, we have a breakpoint that it keeps breaking at, so we'll have to remove it to go down to here. BOK is set to true because that's what we set it to up here. However, in the immediate window, we can say BOK is equal to false. So now BOK is false, and when we execute this line of code, we now go inside of the else statement rather than inside of the if statement, and we display not OK. So the immediate window is very handy to help you debug your code during runtime. I showed you a little bit on how to use the watch window, but let's go into it a little bit more in detail. Let's create some more variables here, like maybe a floating point number and a double precision number. We'll make both of these equal to 3.14. Place a breakpoint right here, so both of these variables get initialized. We'll build the program and run it. And then inside of our autos, we can see we have BOK and D. Inside here, we can't add any variables. Inside locals, we have all the variables that are inside of this current local scope and their values displayed. Under watch, we can specify which ones we want to see and which ones we don't. So we can delete these if we don't want them visible, or we can go in here and type them in or select on a variable and right-click and select Add to Watch. Now notice that both these variables we initialized to be 3.14, however in memory, both of them are not exactly 3.14. The floating point number is 3.140001, and the double precision one is 3.14 with a whole bunch of zeros and then 1. If you're programming your code to do simulations of physics or things like that, the precision of your numbers may play a role in terms of your output. So this here could be an error component inside of your physics engine. If this means a lot to you, then I would recommend not using floating point numbers, but rather using double precision numbers. Double precision numbers use up more memory. As a matter of fact, they use twice as much memory as floating point numbers. However, you notice that the degree of accuracy is much, much better. Inside the watch window, you can also do simple kinds of arithmetic like 2 times f to see the values displayed here. However, you cannot change the values of each of these variables the way you can inside the immediate window. With your watch window, you have more than just one watch window. You can go under Debug, Windows, Watch, and you'll have access to 3 others. So in total, there are 4 watch windows you can open up, and you can have different variables inside each of these. Or you can have the same variables if you want. You can sort of group them depending on how you're debugging your code. If you want to remove these, just hit on the X and it'll disappear. If you want to get it back, you just need to go under the window here and select watch. Let's also take a look at our global variable here. Under the watch window, we'll just type in g_i. We have the value listed as 100 and the type is an integer. If this value had more meaning to you by displaying it as a hexadecimal number, you have the option to do that as well. You can just right click and select hexadecimal display. Now inside of the watch window, all values that are integers will be displayed as hexadecimal numbers rather than regular decimal numbers. So 100 is the equivalent of hexadecimal 64. If you want to go back to regular display mode, just right click and select hexadecimal. Notice that the floating point numbers here don't change whenever you select hexadecimal. This option here makes all the values inside of the watch window change to be hexadecimal or regular decimal display. You don't need to select each one to be hexadecimal. Instead, everything will be switched for you automatically. Let's take a look at the standard template library and the way it works inside of the debugger. We'll just take a look at this std vector class. So to use it, we'll need to include vector. And then down here, what I'm going to do is create an std vector of floating point numbers. And we'll just take one of these for loops and iterate through here, adding values into this array. Okay. We've gone through and we've initialized all the variables inside of this vector to be this value here. To see these visually, all you need to do is select your variable, select on the plus sign, and you can now see everything visually here. This is new to Visual C++ 2005 and 2008 Express. In the 2003.NET, you won't be able to see the output of your standard template library variables very nicely. So here we can see the first value inside of our array is 0, second one is 3.14, next one 6.28, and so on. So everything is very nicely laid out for you and very easy to comprehend what is inside each of these array components. So that's a great new feature within the Express editions of Visual C++. Another really powerful feature within the Visual C++ debugger is the ability to create conditional breakpoints. Let me demonstrate how these work. What I'll do is I'll take this code here, and well, actually no, I'll take this one, and let's just clean some of this up here. Okay, so what I'm going to do is just have a simple for loop that's going to loop 10 times and display 10 lines of text to the screen, like so. If I were to go ahead and place a breakpoint right here and I run the program, notice that the program breaks and the only thing we get here is matic nose. That's because we placed a printf statement before the for loop. If I want to continue running the program, for instance, all the way down to here, I could try to do this, run to cursor, but you notice that it only ran and then it broke again. We only got the one line of text before it hit that breakpoint a second time. What you could do is go under breakpoints here, unselect this checkbox, and the breakpoint is still there, but now it's disabled. So now when we hit continue on through, the program runs and it didn't actually stop. To re-enable it, you can click on that circle to reactivate it, or you could right click on it and you have the option to disable it from here as well. Let me demonstrate how to create a conditional breakpoint. Right click on your breakpoint and select condition. From here, you can specify what condition has to be met before this breakpoint becomes active. Let's say we want to make this breakpoint active after I is greater than 8. Hit OK. You notice that there's a plus sign showing up now inside of the breakpoint. If we run our program now and take a look at the output, look what happens. We ran through 9 times through our for loop before it broke, because the I value had to be greater than 8 before this condition was met, and then we broke. So that's how you would use conditional breakpoints. This is very handy whenever you know that your code ends up crashing or doing something bad under a certain condition. If you can quantify that condition into a statement here, then you can place a breakpoint to cause your program to go into that condition right before it breaks. And then you can step through, take a look at all the variables inside your locals or inside of your watch window to make sure everything makes sense, and you can very easily figure out what's wrong with your code that way. So conditional breakpoints are very handy. Under here you have some other options. You can filter, you can hit count, things like that. If you want more information on this, you can read the MSDN help on breakpoints, or you can just play around with them. For instance, break when the hit count is a multiple of, and then type in some number. So it's pretty intuitive on how these things work. Just play around with them and you can get a pretty good feel for how to debug your program. There's one other thing I wanted to show you inside of this VMK, and that's how to comment your code with smart tags. There's a tab that you can bring up on the very bottom here that's called Task List. If you click on it, you'll see a listing of different kinds of tasks. What you can do is you can make items appear inside of this task list by giving them keywords inside of your comments. Let me demonstrate. We already know we can comment code by using the 2 forward slashes. However, if we add the word to do to our comment line, then you'll notice that if we go inside of the task list here and select comments, then the to do appears right here. And if I type in something here, you notice that it appears inside of this task list. This is very cool because these comments are going to stay with you inside of this task list independent of which file you write them in. So for instance, I also have this stdafx.cpp file in here. Notice that inside of this file I have a to-do as well. So it says reference to additional headers you need in stdafx. This shows up here because we have the to-do keyword showing up. If I go and close that file, you notice that the task list to-do disappears as well. So it's a quick reference to your code if you want to know where a certain location in your code is. You'd normally label your code to-do whenever you are creating functions but leaving them blank for the meanwhile. So for instance, if I were to create a function over here, I don't know, foo, and for now I didn't want to implement it, I would do something like this: to-do add code here. And then later on, when I'm programming down below, maybe, you know, I finished working here, so I can say, okay, I'm done this. What else do I have left to do? Well, I can go to the task list and I can see, oh, I have some other section here of code that needs to be filled in. I can double click on it and it'll automatically take me to where the to-do is located. There are 2 other special keywords that you can use that will show up inside of the task list. You can use the keyword hack and it will show up, and this is usually used whenever you are editing your code and you modify it in such a way that it's not optimal, but it's just sort of hacked so that it will run and you can test it. With anything that you hack, you probably should go back and change it to make it correct for the final release. The other kind of comment tag that you can use is called undone. When you type undone in on a line of comment to code, then whatever you type in here, just like the other to-do and hack, they'll show up inside of the task list. And with undone, you'll usually use this whenever you are deleting code temporarily. You'll label it as undone so that later on you know how to quickly find it just by double-clicking on the task list down below. You have the option to create your own keywords as well, and you can do that by going under Tools, Options. Under the Environment section, there's a Task List option, and in here you can see there's the hack, to-do, and undone. What you can do here is you can add your own keywords that will show up inside of the task list. So for instance, let's say I go in here and type in my name. I'll select Add, and now anytime that I create a comment with my name in it, then it'll show up inside of the task list. This is a great tool if you want to organize your code so that when you're working on a big project, you know how to quickly navigate through it using the special keywords that you have here. So that's about it for this VMK. I hope you learned something. There's a lot of features within Visual C++ that you can use to help you debug. One thing which I should mention that's very important. Anytime you're using the debugger, you have to have compiled your code in debug mode. You notice inside here now, when I'm running, I can go and take a look at all the variables and things like that. Actually, let me put my breakpoint over here. Well, no, that's a bad example. Let me do this instead. I'll create a floating point number, and I'll make it equal to 10.5. I'll place the breakpoint right at the end here so that when I run my debugger and I take a look inside of the watch window for my variable f, I can see it's 10.5. That's great. However, if I take my code and compile it as release, first we'll build it, then we'll run it, you'll notice that the code breaks at the breakpoint, but the variable f is not defined. It's not defined because the compiler wasn't compiling in debug mode. You only have all these special features with the debugger if you run it in debug mode. So that's the key difference between debug and release. In debug, you want to use this feature whenever you're developing your software. You'll be testing it, removing bugs, making sure everything works. Your executable that you're compiling will end up being bigger because it has all this extra debug information embedded into it so that you can see the variables while you're playing around with it in runtime. However, when you compile it with release mode, all that information is not stored with your executable, which means you cannot see the values of your variables, you cannot see your calling stack, you don't have any access to debugging. So by the time you get to the release mode, you should be pretty confident that your program is flawless and there are no more bugs in it. Also, in debug mode, if you do have bugs, Visual C++ will handle them relatively nicely to make sure that your operating system doesn't crash. Under release mode, you don't have that guarantee. So it's always recommended to start in debug mode, build your program, remove all the bugs. Once it's all safe, then go to release mode, rebuild it. You'll have a smaller executable and your code will run much faster. So that's the sort of process you should be going through when you're developing software with Visual C++.